into machine learning frameworks and the fundamental research in fractional order and non-local modeling. So today, Mamikon is going to give us a talk with the title Partition of Unity Networks for Deterministic and Probabilistic Regression. So please join me and welcome our first speaker.
Thank you, Ming-Wang.
Yep.
Yeah, it's good to talk to my old group. Like you said, the talk is about partition of unity networks for deterministic and probabilistic regression, and this is work that I've done with several collaborators at Sandia. So the background of this talk is, let me just minimize this so I can see my slide. The background here is we're going to look at deep neural networks for scientific computing tasks. A prototypical example is solving a PDE, surrogate modeling of some high-dimensional system like a dynamical system, and reduced order modeling, all tasks which involve deep neural networks for regression typically. And there, deep neural networks have been used instead of traditional numerical methods like mesh-based PDE solvers and PCA. The advantages of deep neural networks here, DNNs, it's simplicity, everything is continuously parametrized, they're off-the-shelf HPC codes, and there are some, there's applicability in very high dimensions that would prohibit grid-based methods. The disadvantages that we'll try to address are irreproducibility in some cases, instability during training, a lack of theoretical guarantees, and convergence in practice, high precision in practice, as well as sensitivity to hyperparameters in order to get good results. So the plan in the first half of the talk, we're going to go over a bunch of topics, the notation and stuff like that, and some of the training strategies. So adaptive basis, viewpoints, least squares gradient descent, and box initialization. That'll probably be very familiar to you if you've been working with us on films. So I apologize if you've seen all that stuff before. But in the second half, we'll talk about POU networks and the probabilistic version, which utilize those strategies. So once we go over that, we can just jump right into POU nets. So deep neural networks involve layers of affine transformations and an activation function. So given an activation function denoted by T with a weight matrix W and a bias B, and some activation function which is born as a function from scalar to scalars, a typical feed-forward neural network architecture. This is what you should have in mind throughout most of the talk is has the hidden layer block defined as in this equation. So compositions, alternating composition of affine maps, and the activation function which acts component-wise. So it's been vectorized. And the parameters inside of these affine transformations are called the hidden layer parameters. And typical activation functions are things like the ReLU activation function, which is just a linear ramp, and smooth versions of that, as well as things like tanh. For regression, the deep neural network is typically finished off with a linear layer. So just an affine layer without a bias. And the hidden layer parameter, I think I said they're denoted by this C sub H, and the linear layer, which is just the last matrix, is going to be denoted C sub L. So with those parameters, the deep neural network is an approximation class. Not necessarily a space because of nonlinearity, but I call it an approximation class. It's some parametrized manifold in some function space. The function space will depend on the regularity of your activation function sigma. So if sigma is a ReLU, then your deep neural network with those parameters free parameterizes some function, parameterizes functions, a manifold of functions inside of continuous piecewise linear functions, all continuous piecewise linear functions. And if sigma is smooth, then it's some manifold inside the space of all smooth functions, or your favorite Sobolev space Here I've just shown you the typical way that people represent neural networks using a graph. So these dimensions of these affine maps, the input and outputs don't have to be the same. So there's an input dimension. In this picture, they're all the same. So there's a constant width in the hidden layer. Each of these nodes is a dimension of an input and output of the corresponding affine map. And in this case, for a univariate output, for a one-dimensional output, the final linear layer is just a dot product of your output at the last hidden layer and the coefficient vector for your linear layer. In a classification type neural network, after this final hidden layer, you have a linear layer. If you have 3 classes here, then the dimension of the linear layer, the output, is the same as the number of classes. And you want to interpret the output of your neural network as a probability of belonging to each class. So after the linear layer, you apply a softmax layer, which I've written down here. This is what the softmax is. It's just basically a multivariate logistic function that maps your output into 0 and 1 and sums up the output to 1. So this actually is a probability of belonging to each class. Yeah, and this is exactly what I've written here. For classification, there's a linear layer and then a softmax layer. So for regression, the continuous, when we talk about regression, the continuous version of that is function approximation. So function approximation is at the heart of these deep neural network applications. In regression, you're given finite samples of some target function, and for some points inside some domain, and you want to construct a good approximation to f in some norm, like LP or HS in a Sobolev space. So in a regression problem with deep neural networks, people typically use this mean squared error, which is just a little L2 loss function, objective function. So little L2 over some point cloud, because you can't actually work with the real Sobolev norm. In classification, you try to minimize the discrepancy between your deep neural network output, this distribution here, and some target distribution that gave you some labeled samples. Usually the cross entropy loss is used to train. So we're going to focus on regression, like I said, but the classification architectures that I introduced here will make an appearance. So there's a reason I introduced them. One of the examples we want to have in mind is a physics-informed neural network. So this is like a regression problem, except you augment the loss with the second term here. So you'll have a regression type loss, and then you'll have a PDE residual over what I call our collocation points, and I use the phrase collocation points loosely. These are just points where you want your PDE residual to be small. And as this audience well knows, you can do this using off-the-shelf tools, because you can do derivatives with backprop. This regression term, typically for PDEs, is further broken up into initial a point cloud where you have initial conditions, a point cloud where you have boundary conditions, and then maybe a point cloud in the interior. So you can leverage the PDE and data on you. Of course, there are other types of losses you can do, like Nat here at Sandia has introduced these CV pins, where instead of a collocation type loss, it's a loss that's inspired by a finite volume mesh. And these are just some examples from the classic papers where you can use a pin to basically solve a PDE without using any more information than you would use to solve a PDE, just initial and boundary conditions, and put some collocation points in the interior, or you can put data on the interior as well, like in this example for Navier-Stokes. So that's the background here. So all of the work I'm going to show you, the POU nets and everything, is inspired by this adaptive basis viewpoint. This is how we think about deep neural networks in our group. So if you consider the type of neural networks for regression that I showed you and just think about regression. Just think about a univariate regression problem. Your neural network looks like this, where these phis are the outputs of your nodes in your hidden layer. So with this formula, it makes it clear that the hidden layer parameters, which parameterize everything up to these phis, parameterize a basis. So this is analogous to like a finite element mesh and shape functions that are parameterized by the coordinates of your mesh and the however you chose to parameterize your shape functions. That's basically what the hidden layer block is doing. And the final linear layer are just coefficients for these basis functions. So from a scientific computing perspective, well, I should say I want to strike a balance here. So a lot of the work that I'm going to show you is born of maybe a critical perspective of how deep neural networks are used now. But I want to balance that by saying that there's a lot that we're asking from deep neural networks when we're trying to use them in these numerical methods. So as an approximation scheme, training deep neural networks is a nonlinear type of approximation, like adaptive finite elements, Freenaut splines, and best n-term wavelet approximation. But there's a lot of theory and a lot of strategies for those methods. So you know that if you were to try to solve some problem using one of those numerical methods, you need some domain expert who knows all the pitfalls of your particular problem and so on. Whereas just writing down a pin and running an optimizer, which is easy because everything is continuously parameterized, is analogous to just letting all the parameters in a nonlinear approximation method, like an adaptive finite element method, be completely free, including all the shape function parameters, and just letting a first order gradient optimizer try to figure everything out. Okay, so this is a Herculean task, and so it's reasonable that more work has to be done for neural networks to actually work reliably, to be a robust tool using this approach. I can mention that this analogy to finite elements can be very concrete, can be made concrete. There's a paper from the work from the group of Jinxiao Xu that I've listed here, which compares using ReLU deep neural networks to adaptive continuous piecewise linear finite elements, are adaptive. And I've included a picture here from this paper by Hannon and Rolnick, which is the output of a deep neural network with a two-dimensional input. And you can see this looks like some finite element mesh. The number of sides of each polygon and so on are inconsistent, but this looks like some finite element mesh. These meshes are moving as you train your neural network and try to solve your problem. Right. And as another point of background, I want to say something about the approximation theory. So universal approximation theorems are frequently quoted as why neural networks work in practice. I think it misses the mark because even polynomials have the universal approximation property. That's the Stone-Weierstrass theorem. More relevant are these proofs of approximation rates as the size and the number of parameters of your deep neural network increase. Of course, though that's important, but in general, you can't find those optimal parameters using the deep neural network, using gradient descent, the way that people actually train them in practice. And so the issues there are your various types of errors. There's the approximation error, which is the difference between a loss you realize using training and the globally minimal loss. And then there's the generalization error, which is the difference between your approximation, however you found it, and your target function as measured in your true LP or Sobolev norm, or some approximation to that, some discrete norm computed at a different cloud of points, your test set. So in traditional numerical methods, you can theoretically and practically, you can get convergence of these errors as a resolution of a grid or the order of your shape functions increases, like in an HP method. But with neural networks right now, it's impossible to drive these errors down to machine precision. And typically you will stagnate much earlier than machine precision due to things like bad initializations, unstable training, and hyperparameter optimization. So these are the things we want to improve. So the type of problems we look at are L2 regression problems. This will encompass pretty much every kind of problem we look at in this talk. So just a weighted combination of L2 things. For example, the standard regression just has one term. The pins loss that I showed you has several terms where these L's can be PDE operators. And then if you haven't seen this before, I'll go over this quickly. There's plane networks, which are what I showed you before. And then there are residual networks, which involve basically a bias by the identity. The idea here is that when you initialize a very deep network, these layers will be biased to be close to an identity, so it'll be more stable. And a good rule of thumb is if you have more than 10 layers, you should probably use a ResNet. It really depends on the width of your network as well, but that's a rule of thumb. So the training algorithm I just want to introduce quickly is this least squares gradient descent algorithm. So in order to minimize the loss that I showed you, this weighted little L2 loss, the typical approach is to just hit this entire thing with gradient descent in both the linear layer parameters and your hidden layer parameters. But if you look at this analogy to finite elements to this adaptive basis viewpoint, the alternative is to hold the hidden layers constant and then minimize with respect to the linear layer weights by solving the least squares problem. So if you freeze your hidden layer weights and these just become a fixed basis for this one step, then you get a quadratic loss function in your linear weights. So you can solve that using a least square step in one step and get the globally optimal coefficients for your frozen basis. And that's exactly what this least squares gradient descent step is. It's just alternating the gradient descent steps and the least square steps. Gradient descent for your hidden layer parameters and least squares for your linear layer parameters. The idea here is that if you're trying to get to some good local minimum, well, if it's a local minimum in all the parameters, then your linear layer parameters should be optimal for your hidden layer parameters for that basis encoded by your hidden layer parameters. So any kind of good global minimum will be on this manifold where CL is the least squares solution for the adaptive basis and your data. So if you have some initialization, what you do is you do a least squares step initially to get on this manifold. And the gradient descent steps will take you off this manifold, but when you update your linear parameters, you'll get back onto the manifold. Whereas a gradient descent will try to get to this local minimum just through some arbitrary path in parameter space, a standard gradient descent like Atom. And by the way, in all of our examples, when I say gradient descent, I mean a step of Atom. Atom is the gradient descent optimizer we use. So I don't want to spend too much time on these figures, but in practice, these blue lines here are the least squares gradient descent. We've got various activation functions in various sizes, but your least squares typically trains faster and stagnates at a much better precision. Although not always, I included this figure. You can't really prove anything about it, in case you were wondering. That's the content here. So then I want to talk about the initialization that we'll use for POU nets. And this is what we call the box initialization. So I won't show you all the details. I just want to point out to you the issues with initialization. In my opinion, initialization is the most important issue just in practice. That's what I've observed. So again, think about the adaptive basis perspective. When you initialize a neural network, you're initializing a basis in those hidden layer in the hidden layer block and some random coefficients. Now, you want your basis to have high rank. Your initialized basis should have high rank. That'll make it your initial fit easier, and it'll put you in a better place in parameter space from where you can start optimizing. So the issues you want to avoid are, well, you can illustrate it by just thinking about the simplest network, one hidden layer, which is just a linear combination of ReLUs. So you can initialize a wide network with lots of nodes and say I have a very expressive network, but you have to pay attention to how you initialize. So if all of your data was in the unit box, in the unit interval, and you initialized some biases to the right of your unit interval, then the ReLU functions with those biases are 0 in little L2 over the data. So, and more to the point, the gradients with respect to these biases and with respect to the slope are all 0 as well. So these would be dead nodes. They contribute nothing to your data fit, and your gradient descent optimizer will not recover them. So, you know, the smart thing to do is to sort of scatter your, if your data is normalized, scatter them in whatever box you have them normalized in. And the industry standard initializations, He and Glorat, don't really do this. So those initializations are from image classification. The objective there is to prevent the output of your neural network from blowing up. So those initializations actually put all your biases, cluster them all at the origin. So all your basis functions are linearly dependent, and then they try to control the slope. So like I said, you want to put the biases, scatter them randomly where you have data, or in higher dimensions, you scatter the cut planes of your ReLU function in whatever box you have your data in, and then you can control the slope to control the amplitude of your neural network. And that's the idea behind the box initialization. Without showing you the argument, it's a layer by layer initialization. You can use it with any activation function you want, and this is exactly what I was telling you about the Glorat and the He initializations. All these basis functions are linear, and these are for deeper networks as well. So the box initialization actually gives you linearly independent basis functions. With a plane network, as you go deeper, it sort of degenerates, but with the residual network, you get linearly independent basis functions. And this is just an example of how it works in a simple 2D regression. This is just the He initialization, training on a simple function, I think sine 2 pi x, and you can see that as you increase the depth of your network, the He initialization actually, the answer gets worse as you increase the depth of your network. These are fairly deep networks. So this blue one is the shallowest one, and then they start to creep up. Whereas with the box initialization, you get some consistent improvement as you make your neural network deeper. Not a huge improvement, but actually an improvement, which is good. Okay, I'm running.
Mamikon, can I ask a question here? Because yes. So do people, or you have done like Graham Schmidt at some point when you go deep with a box? So to make it, have you tried to do that?
I didn't hear the question.
To do Graham Schmidt, to reorthonormalize.
We've tried Graham Schmidt, and I think it was very expensive.
Very expensive, yeah.
And I don't think it made a difference with the box initialization. So.
No, I meant, you know, because with the other method, you have to do it all the time. But for you, you sort of get into trouble later on at depth. So at some point, you just do one or two, and you know, you know. Anyway, I was just thinking, like, but you have tried, okay? You have tried.
We've tried it. I can talk to the group and see what the conclusion was, and give you a better answer. It was a year and a half ago when we were still before the lockdown, so my memory's a little fuzzy. I think I'm running behind, so I don't want to talk about this too much, but basically, don't look at all this detail. If you try to solve a advection equation, a linear advection equation with a non-constant speed, what we've shown is the least squares gradient descent gives you a better answer. Basically, it stagnates at as you increase the number of layers, it stagnates at a better root mean square error, and you get something that looks like convergence. I put convergence in quotes. There's fairly large error bars here, but you get some trend of improvement. I think the convergence rate's something like so this is second order with respect to depth, and you follow that for a little bit. But basically, the point here is that the least squares gradient descent, the box initialization can give you these results, but this is still very far from the kind of precision we see with numerical methods. So so now I want to tell you something about classification. I just want to show you some results from classification. Basically, we looked at using solving classification problems with this technique. The classification architecture, because it has softmax layer, will no longer give you a quadratic loss in the linear layer weights because there's a nonlinear function on top of them, the softmax. But the objective function with the hidden layer weights frozen will still be convex. So we can do Newton instead of least square steps. So we have a Newton gradient descent step for classification. And what you see in classification, I mean, is that neural networks are very good at coming up with decision boundaries. This is obviously not our observation, but this is a Peaks benchmark. It's a very simple 2D benchmark, I think, due to the group of Lars Rukoto, where you have 5 classes and some point cloud. When you do the Newton gradient descent, you see some acceleration of training and a 2 to 3% improvement in final validation error for things like MNIST and CFAR. But I don't want to talk about those. I just want to point out that this illustrates that neural networks are, when you use for classification, they're very good at finding partitions of space, finding decision boundaries in high dimensions. This is just 2, but we know in much higher dimensions they work as well. So this got us thinking. What we've been trying to do when we've been using these neural networks for regression to get these results, for example, is we're trying to get the neural networks both to essentially come up with a mesh, so to speak, and achieve some high numerical precision. But after we did this project in image classification, we had this idea that okay, no matter what we do, we can't see these great theorized convergence rates with deep neural networks. But how are those results proved? Those results are proved by showing that a deep neural network can emulate a partition of unity, which localizes approximation, and it can emulate monomials, which can give you very, very precise convergent approximation, and then you piggyback off of approximation rates for things like HP. And that's how those results are proved for neural network. So our idea was, what if we use the neural networks just for the partition of unity part? Because we know in high dimensions, they're good at coming up with classification and partitions and decision boundaries. But then for the approximation, we put monomials on top of that. So we end up with like an HP-like approximation where the POU nets are kind of doing a mesh-free partition of space. And then instead of trying basically hopelessly to get them to emulate polynomials and give us high precision, we just use polynomials because we already have them. So we attach a polynomial space to each of those partitions, and we learn the coefficients as well. So the architecture of this POU net is as I've shown you here. So this block here is exactly the type of classification architecture that I showed you in one of my earlier slides. So hidden layer, linear layer, and then a softmax layer. And then for each node after the softmax layer, we have a you can attach any linear approximation space you want to each node there, to each partition function, but we use polynomials. So the idea, like I said, is to emulate POU plus monomials directly by building in the monomials. So the formula for a POU net is exactly what I've written here. So given some partition of unity, which so far is just arbitrary, there's no neural network here yet necessarily, given some partition of unity, which are just a sequence of functions which sums up to 1, with each function having non-negative values, our approximant is a combination of these partition functions weighted by some polynomial approximation. Okay, where this polynomial approximation is distinct for each alpha, for each partition. So we take V, these P's to be polynomials. I'm repeating myself here, but we parameterize these P's by a neural network. And it's just the classification type architecture just fits immediately into this framework, okay? Because as I told you before, it has these properties automatically by virtue of the softmax. So we consider both a shallow and a real bona fide neural network architecture in our results. So the training algorithm we use follows the least squares gradient descent algorithm very closely. When we fix the partitions here, which are parameterized by the neural network, then we get something quadratic in these coefficients, and we can solve for the globally optimal coefficients here. We can consider various architectures here. So as a basic example, you could just do an RBF net parameterization of our partition functions. So your partition functions would have this form with these center parameters and the width parameters, C2. If you have a simple function, so without a lot of features and it's smooth, then this is what you would go for. If you have a function with a lot of features and in very high dimensions and it's rougher, then you want to avoid this and you want to consider a real deep neural network for your fees. There's an error estimate which actually isn't so useful in practice, but it sort of explains the results you see in practice. So if your partition functions phi had compact support, just imagine that they had compact support, then we can prove an error estimate that says the optimal approximation is basically controlled by the diameter of the supports of your partitions, which kind of implies that if you want to get high precision, then you want you want your partitions to actually be localized. So you don't want your optimizer to kill a bunch of partitions, throw them away from the data, and just stretch out one partition to cover all the data, and then just go back to doing a regular neural network regression. You want all those basis functions to be active and localized to actually see some kind of improvement. And this is what we see in practice when we work with functions without compact support, partitions without compact support, because they train easier typically. But the idea here is actually observed in practice.
Can I ask a quick question here, Mamikon? This is Yan Jong.
Go ahead.
In equation 18, this suggests us that if we want the upper bound to be small as possible, then the optimal support function should be something like, if we are thinking about hypercube, then it should be small equidistant divided the small hypercube, doesn't it? That's what theory also used for the proving some convergence theorem.
Yeah.
And if that is the case, in the light of this fact, I'm wondering in practice then why you might want to train your partition function rather than just employ what theoretically proven to be almost optimal, because we already know that what should be done in partition function, right? So that for 1D example, we can just use the equidistanced partition, and 2D cases, or we can just chopping up our grid, so the making a small support. I think that should also perform almost optimally, right?
Yeah, the issue with that is The use case for this would be some function with a nominally high input dimension, but the features are really concentrated on a manifold of low dimension, on a latent manifold of low dimension. So then you don't want to take just a uniform grid in your input dimension, okay? Because there's a curse of dimensionality there. You want your neural network to sort of discover the latent dimension, and then your covering of that latent manifold might not be uniform in your input dimension. Does that make sense?
Right. I see. Then I think this might be just for the easy presentation. I guess in the actual paper may discuss about this intrinsic dimensionality. Then the effective dimensionality is interpreted as some smaller than the high dimensionality, and the support is then accordingly constructed according to their manifold structure and the smoothness. Is that correct? Okay.
That's the idea. We haven't actually proven. We haven't.
Oh, I see.
That's the idea.
I think that yeah, I think we can discuss later on. I think that can be done some effectively using the manifold construction and geodesic way of the constructing. I think that would support more theoretically support to your construction. Just one comment for that. Yeah, but thanks.
Yeah, sure. Okay. So I'm going too slow through this. So I want to just say that to actually enforce the partitions all being active and helping localize the approximation, we have to basically add a regularizer. We start training with a regularizer to get a good set of partitions. That's what that slide was about. So in this example, we have a two-dimensional input, but the data is a sine function sampled on a latent one-dimensional manifold. So just a cross shape in the unit box. And we use RBF nets because this function is easy, it's a sine. And the idea here is that if the approximation works the way it's supposed to, then the optimizer should move the RBFs onto this cross and sort of localize onto the cross and get them off of, get them onto that latent low dimensional manifold, and that is what we see. So these are rates of L2 error as the order increases, that different curves are different orders, and this is the number of partitions. So on the right-hand side is just a standard MLP with a comparable number of parameters. So not a very large MLP, and there's stagnation at a low precision for that.
Mamikon, can I ask a question here on this one? Yeah, here on the left and on the right, you use the least square GD or not? You use the same optimizer?
I'm not sure. I think this was LSGD, and I think this was, this version of LSGD where we're finding the globally optimal Cs. I believe that's correct. Actually, I'm doubting it. This may just be using regular gradient descent, George. This may be using regular gradient descent.
That's what I was wondering, if the accuracy can go down if you use that LSGD there. But yeah, okay, thanks.
Yeah. Okay, and this is a more challenging example. So this is a function that's rough with lots of features. So here we're parameterizing the partitions using a classification type deep neural network with a softmax layer. So we have different frequencies of our target function, and you can see that a plain old ResNet starts to fail as you increase the number of frequencies, whereas a POU-net, as long as you increase the number of partitions relative to the number of features in your target function, so it can actually localize to each one of these spikes, it continues to do a good fit for both this triangular wave and that squared for this quadratic wave here. So this orange is the POU-net, green is the ResNet, which is failing. Right. This is I think I have to skip this. This is just showing how during the first phase of approximation with the regularizer, the partitions adapt to the features of our function, and then during the second step we turn off the regularizer to get a higher precision. So now I want to talk about the probabilistic version of these networks, which was supposed to be the focus of this talk. But the idea here is that we put a Gaussian mixture model on top of our POU nets. So we can get a probabilistic generalization that we can train, still using a standard gradient descent, but using a maximum likelihood loss. So this can give us representation of both noiseless and noisy data, and the prediction is still just a Gaussian mixture model, which by virtue of being a GMM, it gives you closed form expressions for the mean and the variance. One of the things we notice with this is that training on the likelihood gives you much better partitions of input space without a regularizer. So the framework gives you something like HP convergence without that regularizer. And but by comparison to Gaussian processes, it's kind of an apples to orange comparison, because Gaussian processes are Bayesian, and they're a little bit different. But if you just want to do regression with noisy data and get some spatial uncertainty coming from that noise, then if you compare our method to the probabilistic POU nets to Gaussian processes, then you use the expressive power of neural networks, but you get to sort of skip a lot of the expensive training associated with things like Bayesian neural networks. And compared to Gaussian processes, it typically trains faster and scales much better to large data sets. So I'm just going to tell you that there's a generative model underlying this entire framework, but just skip the first point, and I'll just tell you that basically this gives you a distribution. Instead of telling you a deterministic output y, you get a distribution for the output y over some point x, and the distribution is this Gaussian mixture model, where the mixture coefficients are your POU functions. The mixture coefficients are your POU functions, and the normal distributions of your Gaussian mixture are basically centered at your POU, your deterministic POU Q. Okay, so because this is a Gaussian mixture, because due to the softmax layer, this is a Gaussian mixture, you can write down the mean and the variance of your distribution in closed form. These are just standard formulas for GMMs. And I guess the punchline of all this is you end up with a distribution, exactly what I said. You end up with a distribution for your output, a prediction of your output, where the samples are centered around your standard POU net prediction Q, but then there's a Gaussian mixture model noise term where the Gaussians are weighted by the same POU functions used in your POU net prediction. So to write down a likelihood function, we have to introduce some correlation structure into how, if you're given data at various x's, what is the joint statistics for your predictions over each of those x's? We, just for simplicity, we introduce this independence assumption. This isn't the only assumption you can have. I'll mention other possibilities at the end if I have time, but the simplest thing you can do is assume that the noise around your POU net prediction is uncorrelated at different points. So this sort of takes Bayesian stuff out of the picture, which is the disadvantage here, but the advantage is that it's a very simple likelihood, and so you can define a log likelihood loss just as I've shown you here.
Isn't that a very strong assumption?
It is a very strong assumption, yeah. So we're working on better, we're working on more flexible assumptions. But the prediction is not uncorrelated. So it's not like it's not like a Gaussian process prior where there's no, where your data isn't entering into your prediction at all. The data will enter into your POU-net prediction, but not into your noise predictions, basically. So when you minimize this log likelihood loss, the notation here is that this theta are your POU-net parameters, your neural network parameters here, and then there's a noise parameters on each partition, the mean and the variance of the Gaussian on each partition. And we minimize this using Atom. So, okay, I got to go through this quickly, but we can do an alternating optimizer again, where we just fit the POU-net, the deterministic POU-net prediction using the least squares, and then do a step of our likelihood estimation for all the parameters.
Mamikon, no rush, because we're interested in this part. So okay. Take your time, okay?
All right.
Otherwise, we'll call you back to explain again.
Yeah. Okay, so I can go into a little more detail. So this log likelihood is one objective function. We can optimize our POU-net, the neural network parameters for our POU-net, and the noise parameters, this mean shifting parameter mu and the variance parameter sigma, all at the same time. What we do is by the way, it's not clear from this formula, but these partitions are also inside of this Q, right? Because this Q is our deterministic POU-net part. So the phis are inside of Q, and they're also the coefficients in our Gaussian mixture. So what we do instead is we do another alternating optimization, where first we just do one step of fitting this Q to data. Then to fit that Q to data, we minimize this least squares. We solve this least squares problem. Then once that Q is fixed, we plug it into here, and then we do a step of maximum likelihood in all the parameters here. So that's the training algorithm we use here. What this does for you in practice, if you're just doing a deterministic regression using this, it's interesting how it works. So there's a lot happening in these pictures, but the first column is initialization. The second column is after 1,000 steps. The third column is after 10,000 steps. These are our initialized partitions here. And this is the initial fit. So with just these partitions, okay, I need to back up for 1 second and say that when you're doing deterministic regression using this method, the optimizer uses these uses the wiggle room that you gave it using these distributions, because these distributions are on Y values. It uses that wiggle room to basically cluster Y values of your target function, and then find a partition downstairs that's adapted to that cluster of Y values, which makes sense if you want to, if you're the optimizer is trying to get a good approximation, so it should cluster Y values that are close together. What's bad about that is that will give you partitions downstairs that are not simply connected. So for example, if you have, for example, a sine function that you're trying to approximate, and you use, in this case, what is this, 7 partitions, then it says, okay, the Y values in this part of my function and this part of my function are close. So I'm going to make a partition that's supported underneath those Y values. That's this yellow thing here. But then that's bad for a localized polynomial approximation, because it wants to do, for example, a linear fit here with one slope, a linear fit here with a different slope. So what we do is, after doing some of this partition fitting, we do a PCA-based bisection to chop, to basically post-process some of these partitions and chop them in half. So you can see after we do a step of this PCA, this partition, which was not localized, has been chopped in half. And now we have a separate partition here and a separate partition here. So really our algorithm has several steps. There's this alternating least square step and this alternating likelihood step. And then after that, there's some PCA-based bisections of the partitions that we get. And that's what we've shown you here. One of the issues with this PCA-based bisection is the partition functions are initially smooth, but when we chop them in half, we get rough functions. So in principle, you can alleviate this by doing, after your PCA bisection, to use a smooth indicator function, some smooth approximation to that, instead of just a sharp indicator function to bisect your partitions. So for example, if you do this using spatially heterogeneous noise, in this case, I've just taken I think this is a tanh function. Here we have a tanh function, and I do some white noise where the variance is, the standard deviation is shown by this profile in blue. And these samples are these black points. So if you, I think this is something like 1,000 or a few hundred samples. If you train this using PPOU nets, the optimizer will cluster partitions. It'll balance, it'll try to cluster partitions both where there's features of your function, where the slope is the highest, and also where there's features in your data. So with a small number of partitions, it gives you an okay approximation. As you increase the number of partitions, you get a better fit to the data, so you get a very sharp fit of the data, including the noise band near the origin, and a decent, in this case, we didn't, if we introduced more partitions, we'd get a better fit at these endpoints as well to the noise. On the right hand side,
how do you get the true standard deviation? How did you get that? The blue curves.
I knew it. The true standard deviation is just
what you prescribe.
Yeah, I prescribe like a sine function.
Okay.
So if you do a Gaussian, and by the way, these take a few minutes to train with close to 1,000 samples. If you try to train a Gaussian process on the same example, and you introduce a likelihood term into your Gaussian process to model white noise, then your Gaussian process will be sort of confused by the fact that you have spatially heterogeneous noise, because that Gaussian likelihood is just a single constant noise parameter. And what the Gaussian process will do after it takes hours to train is it will learn some of the it'll learn basically a persistent variance inside of the Gaussian process to try to compensate for the spatially heterogeneous noise. So it'll give you a very, very large uncertainty, an artificially large uncertainty, as you can see here. So this light blue band is the GP standard deviation plus the Gaussian likelihood sigma term. And this should not happen. So if you had trained a Gaussian process with heterogeneous noise, so noise that was the same amplitude everywhere, it would learn that noise very well and basically nail this prediction and give you a very small uncertainty band there and a good white noise uncertainty. And that's not what's happening here. That we were getting something a lot closer to that using our probabilistic POU net. And yeah, so going back to using this for deterministic regression, if you, for example, approximate something in 2 dimensions, this is basically what your partitions do. So before your bisection algorithm, it'll adapt some partitions to the features of your sine 2 pi x, but again, without localized partitions, because the target functions here are close to the target functions here. So after we do a couple of PCA bisections consecutively, then we get localized partitions, and the approximation rates that we get are consistent with finite element approximations when we use linear monomials or quadratic, linear polynomials or quadratic polynomials inside of our POU net. So these are what we would get with, these are the algebraic rates that we would get with finite element approximation for linear and quadratic. If we go to higher dimensions, let's take the same example, which is really a two-dimensional function, but lift it to higher dimensions. So just embed it in 4 dimensions like this, but now train this probabilistic POU net with input dimension 4. We don't tell it that there's a low dimensional latent space where all the features are. Then it actually recovers. So this is the target function where we just project it down into R3. So you can see here there is some low dimensional structure. If we train the PPOU net, it does something very similar to what it does in 2 dimensions. So it finds features such that when you do the bisection, you recover convergence rates. I've plotted here in dashed lines the 2D convergence rates for quadratic and 4D convergence rates in this example. And you can see that except for this one flyer, we actually see roughly the same convergence rates, independent. So it's independent of the input dimension, but dependent on your latent dimension. And so just the last example, I want to talk about an application to a Sandia problem. So there's this, we have a bipolar junction transistor database here at Sandia, which is 121 simulations, finite element simulations with 4,000 degrees of freedom. So 4,000 basis functions, 4,000 coefficients coming from your finite element mesh. And the shape here, these are for different values of voltages at our emitter base and our collector node. So what we did is we used this PPOU net in the simplest possible way because all these simulations look roughly similar. So instead of doing some PCA model reduction, what we did is we applied the PPOU process with just constant basis functions, no refinements, and just 10 partition functions on this training on a loss that concurrently uses all 121 simulations. And the partitions that we get, 10 partitions that we get, are shown here, which you can see are sort of similar to what we have here in this representative example. And so we compress over 4,000 degrees of freedom into just 10 degrees of freedom, 10 basis functions, and we achieve a worst case error of 5%. And the idea here is that we can use this in some of the geometric neural network approaches that Nat has worked out. Some of the graph neural network approaches here to solve problems using this greatly reduced basis. So George, to your question about for future work, to your question about that independence assumption, which is very strong, we're looking at more general joint distributions. The thing is, we want those joint distributions to still have marginals, which are Gaussian mixtures, because those have closed form expressions for mean and covariance. So the approach we're looking at for follow-up work is to utilize copulas, which are a statistical tool for solving the following problem. If you have a bunch of marginal distributions specified, specifically those Gaussian mixture distributions over each point of x, how to parameterize a general class of joint distributions, a general class of likelihood functions which still have those marginals. So the answer to that is not unique. The independent joint distribution is the simplest answer, but there are many ones, and copulas are a way to parameterize a large class of such joint distributions without forcing an independence assumption. And I also want to mention there's people working with NAT who are applying these POU nets to PDE, to PINS type problems, and doing some convergence studies there, kind of like the convergence studies I showed you for simple regression problems. So with that, these are the 4 papers where I've drawn this work from, and these are my collaborators. So I've done this work with my John von Neumann Fellowship in Films, which I'm grateful for. And with that, thank you for listening. And I guess maybe questions. Well, Ming-Lang, you can moderate.
Hey, Mamikon, can I add something? And sorry,
Yes,
sorry
please
to
go
show
ahead.
up late. In terms of the applications where we're applying this stuff, so these are all just kind of like toy manufactured things in order to get a feel for how it worked. But we have this new result like from a couple of weeks ago, where basically we're taking lookup tables from. We have a fire code, something for doing wildfires and things like that, that has a lookup table right now for, you get the reaction rates for the chemistry as a function of however many thermodynamic states you want to try and characterize things by. For that thing, for like a 4-dimensional lookup table, which usually is something like a gigabyte to carry around, and you have one of those for each species and so on, we can replace that with one of these networks. And that's something that's like 0.5 megabyte in order to work with. So even just using, because this stuff breaks the curse of dimensionality, and we have that hooked into Sandia codes now. So this result here that the Mamikon has up right now is actually, in terms of like, in terms of how you can actually use that in a practical sense, it's a super simple idea, but it makes a huge difference. So now people can go, like, they can have 6-dimensional chemistry because they're not constrained by the exponential blow up of the lookup table. So just wanted to mention that they're one of the applications that's kind of exciting right now.
Yeah, thanks, Nat.
Yeah.
Thank you, Mamikon, for your excellent talk. Is there any questions for our speaker?
Can I ask one?
Please.
Yeah, thanks for the nice talk. For high-dimensional task, so I think one of the core components of the POUNet is applying the use of the polynomial in the specific regime to get the least square solutions. But in high-dimensional case, how do you construct the polynomial? Do you only use the degree 1, or is in high-dimensional case that the constructing polynomial is not an easy task? So
That's a good question. I think it was just second-order polynomials, and for this example, it would be second-order polynomials in 4 dimensions.
Yeah, 4. I don't know. 4 seems to me is not very. I mean, it's doable, of course, in the constructing polynomial. I think up to 10-dimensional case, I think constructing polynomial degree up to moderate degree would be fine.
Yeah, that's a good point. So if we're talking like millions of, thousands of dimensions, that would be a problem, unless there's something I'm missing, Nat.
I mean, you can do it, of course, right? There's nothing stopping you from building the matrix and solving that least squares problem. But you're right, the dimension starts to explode as you go to moderately high polynomials. So in general, for things higher than like order 1 dimensions, we use linear polynomials, and then the complexity goes like d plus 1 times the number of partitions, right?
Yeah.
And that's fine. The other thing that we do for high dimensional problems is we use this together with an autoencoder. So you can train an autoencoder to identify a latent low dimensional space, and then you can use the POU, but the input to the POU is the local coordinates, not the ambient coordinates, right? And then in that case, it's basically turning it into a low dimensional problem, and then it's okay to use high order polynomials again. There's a lot of like pathologies that kind of pop up when you wanted, like any numerical scheme. When you go to high order polynomials, it starts to get a little bit tricky about how reliable it is, and if you're going to get Gibbs phenomena and things, overfitting, all that kind of stuff. So actually working with linears tends to be more robust. And for the engineering stuff we do, oftentimes we just stick to that.
Yeah, I think that makes sense. Another question is, how do you choose the M? I think that the choice of M seems to be quite crucial to get a performance. I think that in general, M shouldn't be very large compared to the intrinsic dimensionality. So is there any rule of thumb that you guys found empirically worked well? I mean, theoretically, it should be like some H to the D, right? But we cannot go that far. So can you give us some rough numbers on what specific number did you use for your examples?
Yeah, so for this example, this example was kind of cheating, you can call it, because I'm sorry for the different notation. This N here, I think, is this N part is what was capital M in
partition, okay.
Number of partitions. Here we're kind of cheating because as we increase the features in our target function, we're increasing the number of partitions. Yeah, I don't know if there's a good way to choose them. I guess what I want to say is that in our experience, that the quality of our answer improves pretty reliably with M. So
Mamikon, it seems that if you go back to that example, it seems that you use a Nyquist frequency. That's
the point of this example, right? Is you want to show that if it scales with the number of features, right? So in this case, you need at least as many partitions as you have piecewise linear.
Yeah, so you have Nat, you have 8. You have 8 wave numbers, and you have or the Fourier is the same thing, 2 points per wave number, 2 partitions per wave number.
Exactly, but that's the point of this, is you want to see that you don't need to over parameterize in order to catch this thing, right? So this is like the smallest possible neural network that could catch these waves. And that's why we did the study where we're increasing the number of partitions together with the Nyquist, right? Like that's the point of this result. The point of trying to do, I mean, of course, this is like any finite element thing, right? Like whenever you build a mesh, what's the correct number of elements that you're going to do? At some point you have to pick a mesh, but the reason we were hunting for this convergence property, right, that you get something like HP convergence, is you'd like to just like take a guess, like, I don't know, you start with 10 partitions and you'd like to see, you double the partitions, you see if you get the same answer, you double the partitions again, and then you can do grid refinement, right? That's why we were looking for this convergence property, because that grid refinement study is like the cornerstone of V and V usually. So, you know, it's not satisfying from a theoretical perspective, but practically that's why we've been hunting this, this convergence property. Yeah, you're right. You know, you want n to the -1 over d, where d is the latent dimension of the data. That would give you something like a quasi-uniform partition of your data.
Yeah, in that example that we were just looking at, if you increase the number of partitions beyond a point, your answer will stop improving. So but one of the benefits here is that you can, so if you're just doing if you're just using a black box neural network, a lot of the times you'll just start getting a worse answer as you increase the number of parameters. Whereas for something like this, you would get the answer would improve as if you didn't have the function in front of you. The answer would improve as you increased the number of partitions, and then it would basically stop once you were able to nail this function. So it depends on your budget.
Mamikon, can you say something? Probably have to move on, but can you say something about the cost of the probabilistic part compared to the deterministic, and how does it scale with? I know you talked about cache of dimensionality, but can you say something about that?
It's identical.
It's identical because so the least square step is the same. We do a least square step. Remember, for the probabilistic one, we alternate between doing a least square step, just like for the deterministic POU net, and then doing a step of our likelihood. So the least square step will scale the same, and then the likelihood was not the dominant part during our training. So
but I mean, the whole point of this probabilistic stuff is that you can derive this log likelihood function in closed form, and now you throw atom at it, or whatever your gradient-based optimizer is, no different than you would throw it at a mean squared loss. And so that the really nice thing is just how many analytic formulas pop out of this relatively simple noise model.
right. So yeah, exactly. All these variance bands are coming from a closed form formula. They're not. There's no linear algebra you have to do to get these variance bands, like you would have to do with the Gaussian process. So.
Have you done high dimensions in probabilistic?
We went to 4 dimensions in this example.
That's deterministic, right?
No, this okay. So this is probabilistic POU nets, but on a deterministic example. So we're leveraging that the probabilistic POU nets are good at finding partitions. There's something about this log likelihood that really helps them find partitions that are very tailored to your features.
Okay.
And so we use them in this deterministic application here. It's kind of amazing that they work out of the box finding good partitions without any kind of regularization or tuning parameters and stuff like that. So and Nat I think mentioned he's doing some 6-dimensional example. So,
but nothing like super high dimension for this 4 to 6 whatever dimensions is as far as we've pushed the probabilistic stuff. But like we said, it doesn't depend on the dimension in any way. So you can, in principle, you could do this in 1,000 dimensions. It wouldn't slow it down. It just might not give as good of an answer.
Yeah.
Thank you, Mamikon. That was great.
Yeah, thank you.
All right, thank you, Michael. So our next speaker is Aniruddha Bora. So Aniruddha Bora is currently a PhD student at Louisiana Tech University in the field of applied mathematics under the supervision of Dr. Weizhong Dai. His research is focused on solving heat conduction equations in double-layered structures. So today, Aniruddha is going to give us a talk with the title Neural Networks Method for solving parabolic to temperature microscale heat conduction in double-layered thin films exposed to ultra-short-pulsed lasers. So please join me in welcoming our second speaker.
Thank you, Minlang, for the introduction. Can I share my screen?
Yep.
Yeah, okay. Hi, good afternoon, everyone. Today, I want to, my name is Aniruddha Bora, and I'm doing my PhD in Louisiana Tech under my advisor, Dr. Weizhong Dai. So today I want to present our paper, which is the neural network method for solving the parabolic to temperature model when double layer is exposed to an ultra short pulse laser. And so my outline of the talk will be with some little bit of introduction, and then I'll talk about the neural network method, and then I'm going to talk about the convergence analysis. Then I'll discuss a few numerical examples, and then I would like to conclude my talk. So let's start with the introduction. So when we say ultra short pulse laser, so these are lasers which emit very short pulses of light. generally in the order of femtoseconds or picoseconds. So it's a very short time interval. For example, light takes around 1.2 seconds to reach from moon to earth, but in one picosecond, right, light travels actually around 0.3 millimeter. So because of this, it has a lot of application. So usually, like whenever this kind of lasers are used for metal ablation, so there is almost no collateral damage when you are in the precision. So this kind of lasers are applied in biology in many kind of surgeries, like for cancer surgery or eye surgery, and also in many kind of semiconductor industries where they want to work with the thermal processing of materials. So in this kind of laser, there's one characteristic that whenever it's used in metals, there is a high rate of heat flow from the electron to the lattice, and that happens in around in very short interval of time. And basically what happens, the initial energy is actually absorbed by the free electrons, which shoot up very high in temperature, and then later is transferred to the lattice. But because the specific heat capacity of electron is very small, and the finite time of the electron coupling factor of the lattice, the electron temperature actually rises very high while the lattice still remains cold. So there is kind of two temperature in this model, and that's why the equation that actually models this kind of heat mechanism is known as the parabolic two temperature model. And this model was first given by Q and Tien in 1994, and this model looks something like this. So here the TE represents the electron temperature, the TL represents the lattice temperature, the G is the electron lattice coupling factor, and S is the laser source term, and CL is the specific heat of the lattice. So now here, this KTE over TL, it represents the thermal conductivity that's actually varying according to the temperature. And this kind of modeling is only for the cases when the electron temperature is less than the Fermi temperature. And similarly, the specific heat of the electron is proportional to the electron temperature. That also holds when the electron temperature is less than the Fermi temperature. And for the laser source term, it's we are using the general Gaussian kind of expression for the laser source, where the TP is the pulse duration of the laser, the delta is the penetration depth of the laser, the R is the reflectivity of the surface, the J is the laser fluency, and yeah. So now, why we need layered structure? So usually in most of the
Can I ask a question?
Yes, sir. Yes, sir.
The second equation, so there's no diffusion in the lattice?
Oh, no, sir. Yeah. Here there is no diffusion in the lattice because during this kind of heating, most of the heat is actually transferred by the electron. So there is no diffusion term in the second equation. So more heat is transferred through the electron rather than the lattice vibration. So that's why
so it's because of the separation of scales.
Yeah.
The diffusion is too slow, so you neglect it.
Yeah. Yes, sir.
I see. That's kind of interesting. Yeah.
Yeah. So layered structure. So we know that in most of the applications, actually layered structures work far more better than single layers. And even when you are considering like surgery of human tissues or eye, it's not a uniform layer, but it's a layered structure. And even when manufacturing semiconductor devices, you have more than one material that is in together. And also, for example, in gold coated mirrors, which are used in laser system, they use double layer. So there's a lot of application of the double layer structure. So the heat transfer in this kind of layered structure, when you are exposing to ultra pulse short laser, is very important. And there are actually many methods to solve that. We have the finite difference method, the finite element method, the boundary element method, and there are a lot of combination of hybrid where you use the finite volume, finite element. And actually, I solved the same problem using the finite difference method, and I came up with a scheme of fourth order convergency, which solved the same equation. So that's where lies one of the motivation for why I wanted to use neural network. So right now is the era of artificial intelligence, and data-driven scientific computing are focusing a lot of research, and especially the physics-informed neural net that was introduced by Dr. Karnadakis and his group was the main source of motivation for me to actually switch from like numerical methods to something like this. So because when I was working with the finite difference method for solving this problem, so it's not that simple. It's a huge derivation and a huge set of equations, and the terms get more and more complicated. So there's a lot of time that actually is dedicated to solve the problem and then analyze the results. So I feel like this kind of technique that was introduced by Dr. Carnegie is like a boon in the science, because now people, if they can use neural net to get the solutions, they can focus more on the problem rather than the technique of solving the problem. So that was the major source of motivation, and my objective was to solve the same model using the neural network to see if I can get it done. And the paper where Dr. Carnegie is introduced this method is cited right here. So now let's get to the neural network method. So for double layers, it's the same sets of equation that I showed before, but the only thing it will be repeating for both the layers, and as well will have an interface condition. So now these are the same sets of equation that I described before, but now I use the notation of m. So m equal to 1 will represent it for the first layer, and m equal to 2 will represent it for the second layer. And that's the heat source term with the initial condition and the boundary condition. So we assume the boundary condition to be Newman, so that like we assume that there is no heat loss in the boundaries. And this is the interfacial condition for the problem, where the first condition actually states that the electron temperature in the first layer is equal to the electron temperature in the second layer at the interface. And the second one actually it actually tells that there is a perfect thermal insulation, so there is no heat loss when the heat is getting transformed from the first layer to the second layer. And this is just for the representation. And as I said before, so CE, the specific heat for the electron is follows something like this expression whenever the electron temperature is less than the Fermi temperature. And same goes for the thermal conductivity, which
I have a question here.
Yes, sir. Yes, sir.
Do you need for the second equation for the metrics? Why do you need boundary conditions since you don't have any differential operators?
Like this equation?
Yeah.
Yeah.
You don't need boundary conditions.
Oh, yeah, but like, yeah,
you impose boundary conditions.
Yeah,
on the
so
left.
this,
on the here and the
this
right.
one, yes, sir.
But remember, you kill that operator. Therefore, you shouldn't be using it.
Actually, you're right, sir. Yeah, but like we were trying to compare our result to the ones that they publish in their paper. So they were using the same boundary conditions. So we were just trying to like match it. But yeah, I see. Like
but mathematically, it's not correct.
Yeah. Usually, this equation is not required because there is no diffusion term there. Yeah. And so now, as far as I have understood, like for neural net to catch a very high spike, it's very hard when there is several thousands of temperature jump, and this kind of temperature jump occurs in this kind of problem. So where the temperature actually jumps for something like from room temperature to several thousands, like around 4,000 Kelvin. So for that, we had to come up with a dimensionless transformation for scaling down the equation. So we used this transformation right here, where the X capital L is the total thickness of the material, and T capital T is the total time that we are solving it for. Now, there is one thing I would like to point out here, that usually these two terms, the temperature of the electron and the lattice, that the transformation that we have used is not just like the scaling down, but there is a subtraction term here. So the major motivation behind using this kind of transformation was that in the problem, if you remember, we had the K TE over TL. Now we are using neural net to approximate the TE and TL. Now, as it gets randomly optimized, there is a chance that TL might actually go very close to 0, and the loss function blows up. So that's why we introduce this term here. So when we transform it, there's a +1 term in the denominator, so that no matter how much like how much small TL gets, it's the loss function is still not going to blow up. And these are the terms after the transformations, and we get the exactly the same equation, but now those terms are scaled down, and these relations hold, which we denote here. And then our source term, the initial condition, the boundary condition, and the interfacial condition. So the neural network structure that we have used here is looks something like this. So we use for layer one, we use for each layer actually we use two neural nets, and we use the first neural net to approximate the electron temperature, which I represent here by U1, and V1 is representing the lattice temperature, and similarly U2 and V2. So there we have the coupled equation. So PD1 actually represents the first equation, and PD2 represents the second equation, and so on for the second layer. And then the loss function is compromising of the initial plus boundary and the interfacial condition altogether. And each neural net that we have used is a fully connected deep neural net, which we all are familiar with the structure like that. Now, the neural net structure is now having 4 neural nets. So I'm representing theta 1 as the parameters from neural net 1, theta 2 the parameters from neural net 2, theta 3, theta 4 on the in the same lines. And the loss function that we have compromise of, as I showed before, is compromising of the PD itself from both the layers and the initial condition, as well as the boundary condition and the interface condition. And for each of the losses, we have just defined it as the discrete L2 norm, where the loss initial condition is given by this, boundary is given by this, and actually is representing the number of training points we choose for the initial boundary and for the interface condition here, and also for the PDEs. So the optimization, as well known, we use the combination of Adams and LBFGS, which is like, I tried to switch them to some different algorithms, but I saw like the combination of this was giving the best results, and has been widely used by many people. And I feel the reason is like Adam helps somehow to go to the global minima most of the times, and LBFGS helps to fine tune the loss at the global minimum basin. And the basic algorithm is like, we set the random parameters, then we set the maximum iteration for both the method, the Adams and the LBFGS, with n1 and n2. Then we are randomly selecting the training points, and if the loss itself is small in the first calculation itself, then there is no need of the optimization. But if it's not, then we go with the Adam optimization, and then we pass it to the LBFGS. And once we get back the results, we are transforming it back to our dimension variables and comparing the solutions. Now, the main thing that we have implemented is in this algorithm is something which I want to show you in this picture. So now in this kind of heating, there is a high pulse in the very first time interval. So the basic idea that we use here to solve it is actually, for instead of solving the whole PD for the whole time domain, we splitted it into time intervals. And then what we did is we tried to catch the pulse in the first time interval, whenever the pulse is occurring, and then we solve it for that time interval. And then once we get the solution, we use it as the initial condition for the next time interval, and then we use a neural net structure to solve that, and then pass it on to the next interval. So the benefit of using this kind of structure was that we were easily able to catch the pulse, and once the pulse was caught, it was very easy to solve the rest of the temperature. But if you were trying to solve it for the whole time domain, it was kind of very hard to get the structure, because this temperature variance is very high, and as we can see later in the numerical results, that there is very high spikes involved. So that's the basic idea we use for solving the model. Now let's go for the convergence analysis. So since our loss is very small and the training points are randomly selected, so we can assume that the neural net solution is actually solving the equation with some error, which is small. So based on this assumption, so the neural net solution Vm for the electron and lattice is actually satisfying the equation with this error terms right here. And since the total loss is very small, so we can assume that the maximum of this is also a small number. It might not be epsilon, but it might be epsilon times a constant here, but still it's going to be a very small number. So we use this assumption for our proof. So for the proof, we actually state the theorem here that if TE and TL are actually the analytical solution for the equations, and we denote the UM and VM as our neural net solution, and since we are using a 10H for our activation function, which is infinitely differentiable, is smooth, and our loss function, total loss, is actually very small. So we assume that the EEM represents the difference between the temperature of the neural net and the analytical temperature, and EL as the difference between the neural net lattice temperature and the actual analytical lattice temperature. And we solve it for the constant case of CL, CE, and KE, and we try to show that the integral of this error function over the whole domain is actually bounded by a small number, where A is a constant. So as said before, our assumption, since it's hold for our neural net solution, and the actual analytical solution solve it exactly, so when we put the error function, it'll have the same kind of error for the equations, and so on for the initial boundary and the interface condition. So now the approach of the proof is something we use like basically for energy conservation proof in physics. So we just multiply the error term of the electron with the first equation and the error term of the lattice with the second equation to get a squared quantity, so that we can get a total derivative of that and show it that it's bounded with the quantity. So after multiplying it, so that's the expression that we get. And now what we try to do is, first of all, we try to get a bound for the interface term right here, which is shown here. So what happened is, now the neural net solution is smooth, and we are considering a closed interval. So according to the extreme value theorem, so that will imply that this term is bounded, and we can actually safely assume that the interface term is bounded by a small number times some constant here. Now, using the Cauchy-Schwarz inequality, the integral term that were on the right hand side is, we can actually group them together and set a bound for them using a small epsilon here, and for the and the B2, which is actually we are using this quantities here, so that we can get this structure in our right hand side. So the basic idea is that we want to show that the derivative of something here is bounded by the term itself, so that we can integrate it and calculate a bound. So we denote d of t as this term which is shown here, and then we drop all the positive terms in the left hand side, because if something is smaller than something and then there is some positive term on the smaller side, we can always get rid of it, and still the thing will be smaller than that. So actually that whole thing gets reduced to this. Now as we integrate it, we get the term right here, and as we move on and integrate it with respect to time, and we get this bound. And since CE and CL are constant, as I said before, we proved it for the constant case. For the non-constant case, it's kind of similar, but it's a bit more it will get a little bit more complicated. So the D0 will be actually bounded by this term right here, and we have that we finally show that whatever we stated in the theorem, that this total integral is actually bounded by a small number, where B4 will be the minimum among all this term. And then that shows that actually the neural network solution will converge to the right numbers. So now let's talk about the numerical example. So we discussed 3 cases here. So for this case, we actually are considering a 50 nanometer gold layer padding on a 50 nanometer chromium layer exposed to an ultra short pulse laser, with the pulse duration to be 100 femtosecond, and the reflectivity of the surface is 0.93, and the laser penetration depth is 15.3 nanometer. Now this is a practical problem, so they use this kind of gold layers for in lasers. So why they use this configuration? So they use gold for its high reflectivity, and they use the chromium layer to actually protect the gold layer from getting damaged by the laser. So what happens is, like, whenever the ultra short pulse laser gets heated, so there are two kind of opposite competing processes. So one is the electron lattice thermalization, that actually the transfer of energy from electron to lattice takes place, and the other is the energy diffusion through the random motion of the electrons. So these two competing effects have opposite effects on the lattice temperature. So a strong thermalization actually implies for a more localized lattice temperature and a higher value in the lattice temperature, whereas the stronger energy diffusion spreads the lattice temperature over wider domain, but the rise in the lattice temperature is less. Now, due to the small heat capacity of the electron, as I said before, the diffusivity is very high, and in around the electron temperature, in the very few femtosecond, it actually reaches the 50 nanometer of the gold. And when it reaches the chromium layer, now the chromium has a very high electron lattice and thermalization coupling factor. So what happens, that electron temperature is actually absorbed by the lattice, and what happens in the process, the lattice temperature of the gold remains almost constant, and the entire energy is absorbed by the chromium, and so that way it protects the gold layer from getting damaged. So the three cases that we have actually considered is the linear one dimension with the laser fluency 13.4 joule per meter square, the nonlinear one dimension with the laser fluency 500 joule per meter square, and the nonlinear two dimension with the laser fluency 500 joule per meter square. Now, whenever the laser fluency is very low, the term that, if you remember, like the thermal conductivity was KTE over TL, but that reduces to KE whenever we are using this less amount of heat. And the thermal properties of gold that we have used here is from this paper itself, where they have published the experimental results. So here we can see that the electron lattice coupling factor for chromium is much higher than that compared to that of gold. So that's how that electron temperature, like the energy from the electron, is absorbed by the lattice of the chromium in the second layer, and that actually is protecting the gold layer.
How is G measured? Is G a parameter that can be measured? The parameter?
I'm not sure about the answer, but what I read about was that this G actually is constant for whenever the temperature is below Fermi temperature, but above that they have actually some kind of there are some variation in the G. It's not a constant number.
It must be empirical. There's no way they from experiment or fit. There's no way. It's not a parameter. It's a coupling parameter. It's very phenomenological.
Yeah. So yeah, that they use this number for as long as the electron temperature is actually less than the Fermi temperature. But yeah, as it goes beyond Fermi temperature, it's not a constant number. Yeah, and we just selected these values because we were trying to compare our results, like which they had. And so okay, so for the linear one dimension, we divided it into two intervals from 0 to 0.5 picosecond and from 0.5 to 1 picosecond, and we did it till 1 picosecond to just compare the results because they had the results till 1 picosecond. And for the first time interval where the pulse occurs, we divided the grid of x and t into 400 cross 400, from where we selected 80 initial points, boundary points, and interface point. And from interior, we selected randomly 25,000 points, and we used a hidden layer and unit, like 11 hidden layer with 150 units each. And we did a iteration of 50,000, 50,000 for both Adam and LBFGS to get a final loss value of 9.6 into 10 to the power minus 6. Now, once this part was solved, we used the result as the initial condition for the next time interval. And then we had to select lower resolution grid points. So we selected 50 grid points from the 100 cross 200 grid with 20,000 points in the interior. and we kept the same configuration for the hidden layers and units, and the iteration number to get a loss value of 7.3 into 10 to the power minus 5. Now the results look something like this. So that's the electron temperature, and the first 50 nanometer is the gold, and the second 50 nanometer is the chromium, and each graph here actually is representing a different time shot. So the dotted one here is the 0.2 picosecond, the straight line here is the 0.25 picosecond, that's the 0.5 picosecond, and that's the 1 picosecond, and that's the lattice temperature. So this first layer is the gold layer, and the second layer is the chromium layer, and we can see that the lattice temperature of the gold almost remains constant, whereas the lattice temperature in the chromium gets a high rise. Now that's how they protect the gold layer. Now this is there's something I noticed, but there's no theory for it, but from my intuition I felt something like whenever we can see here that the lattice temperature is not jumping that much, so it's just a jump of like around 12 Kelvin, and whereas the rest of it it's almost around the 300 level. So what I saw that the neural network actually needed more layers and units to capture something like this kind of pulse, where there is a very small change in across the whole domain and where everything remains constant. Whereas we used very less number of layers and units for catching the nonlinear high pulse. So I don't know if I'm right, but I felt like the neural networks are I think they can solve the nonlinearity more easier than the linearity. That's what I saw from what I got when I was trying to solve it. So that's the electron and lattice for the linear case.
Can I, so from this, I think
Yes, sir.
it's clear that by dropping that term, the diffusion term, now the TI becomes an L2 function, right? It's the discontinuous function.
Yes, sir.
As opposed to T, which is still the C0 function.
Yes, sir.
Okay, and you didn't notice any overshoots. This is the neural network output, what
Yes,
you're
sir.
putting here?
Yes, sir.
So there's no overshoots, undershoots. You get the discontinuity right.
Yeah.
Okay.
Yeah. So that's the linear case. Now for the nonlinear case, we divided into like three time intervals, and the first time interval was from 0 to 0.7. The second time interval was from 0.7 to 1.2, and the last was from 1.2 to 6.2. Now there's a shift of 0.2 here, because the original paper which published the result, the initial condition was at minus 2 TP. So we just shifted it by plus 2 TP. So instead of 0 to 0.5, we just shifted it to 0.7. Now this is the first time interval where actually the catching of the pulse occurs. So here again we needed some higher resolution point to catch the pulse accurately. So we had a grid of 400 times 500 in X and T, from where we select 50 random points for the initial, boundary, and interface, and 10,000 points for the interior. And we use the hidden layer units of 4 layers with 100 unit each, with the iteration of 50,000 and 50,000 for both, and we get a final loss value of 4.7 into 10 to the minus 5. Now you can see that to catch that nonlinear high pulse, we took actually lesser number of points and lesser number of hidden layers and unit to catch it. Whereas for the linear, we had to use like far more number of hidden layers and unit than this one. So now once we got that result, we feed in it as the initial condition for the next time interval, where we use the lower resolution grid points, and we select 50 grid points from X and T for the initial, boundary, and interface, and 10,000 for the interior. And then we use 4 hidden layers with 80 units each, and we use the same number of iteration as before, and we get a final loss value of 6.2 into 10 to the power minus 5. And then we feed in it to the next time interval, and we use grid point. Like in this one, we use a little bit larger grid point size, like grid resolution, than the previous one, because the time interval is longer than this. So so is the reason for choosing a little bit more higher points and layer. So here we use the 50 grid training points for the initial, boundary, and interface, and 20,000 points for the interior, and the same number of iteration to get a loss function value of 3.4 into 10 to the power minus 5. And for nonlinear, so these were the electron temperature, and again this is similar to like the previous graph with each line actually representing the different time levels. And so in the nonlinear case, the temperature actually rises much higher, which is like around 3600 around, and then it takes around 6 picosecond to actually go back to the room temperature, and that's the lattice temperature. And now we can see that there is such a high jump in the lattice temperature in the nonlinear case. So it shoots up to like almost 600 Kelvin. And again, each graph here is representing a different time snapshot.
How have you validated these results?
Oh, sir, like I have we have the results from the paper which they published. I can show back that result.
Okay.
You want me to show it now or?
It's okay. No, just keep going.
Oh, okay, sir. Yeah. So, and there's the electron temperature profile and the lattice profile at the various time for the nonlinear one dimension case. And now for the 2D, what we have done is we have selected a 50 nanometer cross 1000 nanometer gold layer padding on a 50 nanometer cross 1000 nanometer chromium layer exposed to the ultra short pulse laser with a laser width. Now, since it's a two-dimensional problem, now we have the laser width in the y direction, which we select this number, and is the same equation now, but we'll have an extra diffusion term in the y-axis, and the source term will have the y term right here, and the same kind of initial condition, but now we will have 4 additional boundary condition because of the extra dimension. And the interface condition remains same because the interface occurs in one dimension itself. So in y direction, there is no interface. So for this one, what we had to do is we divided it into 4 time intervals. So for the first time interval, it was from 0 to 0.7, where we catch the pulse, and we had to use very high resolution grid point here, where x, y, t we divide into 1200 cross 500 cross 500. With initial and boundary interface, we select 400 random points from this grid point, and we select 35,000 interior points, and we use 5 hidden layers with 100 units each, and we had to set Adam to 100,000 iteration and LBFGS to 50,000 to get a loss function value of 5.89 into 10 to the power minus 6. And once we get this result, we plug in it as the initial condition for the next time interval, and we can see now that how drastically we can actually choose lesser number of points. So the more dimension it get introduced, the more beneficial, like the advantage of dividing into time interval came into the picture. So from here we use like 150 grid points for the initial boundary and interface, and 10,000 points for the interior, with 5 hidden layers and 100 units each. And we use 50,000 iteration for Adams and LBFGS, and we use the final to get a final loss function value of 2.5 into 10 to the power minus 6. And then we plug in into the next time interval, where we kept the same grid resolution, and we selected the same number of points in the same configuration with the same iteration to get almost like exactly almost similar kind of loss function value. Now we use this as the initial condition for our 4th time interval, which is from 2.2 picosecond to 6.2 picosecond, and we kept almost the same configuration to get to a final loss function value of 6.2 into 10 to the power minus 6. And this is the result at the cross section, like wherever the laser hits the laser. So it's that portion. So that at y equal to 500 nanometer. So in the center of the material, and it almost matches the one that we got for the nonlinear one dimension. And as you can see, it's behaving the same way, that the lattice temperature in the gold layer actually remains almost the same, and whereas the lattice temperature in the chromium layer shoots up high. And again, each graph is representing a different time interval, snapshot. So just showing the progress of the graph according to the time. Now, those are the contour plots for the electron temperature. So the first one is at 0.1 picosecond. The second one is at 0.5 picosecond. The third one is at 1 picosecond. The fourth one is at 2 picosecond. And then the last one is at 6 picosecond. And those are the electron temperature, and all the temperature this is in Kelvin. And then these are the lattice temperature. So that's so the first one is for 0.1 picosecond. The second one is for 0.5 picosecond. The third one is for 1 picosecond. The fourth one is for 2 picosecond. And as you can see, the lattice temperature for the gold almost remains like around room temperature, and that's for the 6 picosecond, which is like confirms the graph in the nonlinear too, that the lattice temperature is the highest around 6 picosecond and least in the 0.1 picosecond. Now for the conclusion, so we have presented a artificial neural network to measure the parabolic 2 temperature model in double layered thin films. We have analyzed the convergence of the solution to the analytical solution, and then we have predicted the electron and lattice temperature in the gold chromium film, which is exposed to an ultra-short pulse laser. In the future, what we want to do is we want to extend it to a more complex geometry, and also want to try to solve the parabolic n temperature model, where each n is an energy carrier in the material. So now let me show the, okay, before that, I would like to thank Dr. Karnadakis for giving me this chance to present this paper in this prestigious seminar. And also I'd like to thank my group members, Dr. Wei Dai, my advisor, professor, my collaborator, Dr. Joshua P. Wilson, who is adjunct lecturer, and Jacob Boyd, who is a PhD student in the same university. And let me show the results of the, okay, so that was the result for the linear one dimension, and for the nonlinear case, that was the nonlinear, and this is for the nonlinear case.
They look the same, but is it exactly the same, or do you get some differences?
Very small differences, but looks almost like exactly the same behavior.
Okay.
Yeah. Yep. And yep. So thank you, and any questions, please.
Let me ask another question.
Yes, sir.
When you did the convergence analysis, did you assume that the TI, the matrix temperature, is L2? Okay, you didn't assume smooth field, right? It was an L2.
Yeah, yeah. Mm-hmm.
Okay.
Yeah.
Yeah, that's a very nice piece of work.
Thank you, sir.
Great. Yeah.
Is there any other questions for our second speaker? Thank you for your wonderful talk, Aniruddha. So that's it. So that's the end of our this week's seminar. So everybody have a good weekend. So I will follow with the Zoom link and the recording of this the seminar in a later email. So yeah, everybody take care.
Thank you so much. Yeah. See you. Thank you.
Bye.